All right, so this is our last section in this unit, so just a reminder that your test is going to be next class. But we're talking about the intermediate value theorem today, which basically answers the question, why did the chicken cross the road? So we all know that the chicken crossed the road because he had to get to the other side. Now, if I draw you a lovely picture of a road, and I draw you a lovely picture of a chicken, if the chicken needs to get over here, he's got to take one path, right? He's got to somehow walk his way over because chickens aren't very good flyers. So if he's going over to the other side of the road, at some point, no matter which way he goes, he's got to cross the road. He can't get to the other side of the road no matter how he goes, even if he walks around crazy. Eventually, to get to the other side of the road, he's got to cross over the road. So the intermediate value theorem tells us that if we have a continuous function with a negative value and a positive value, at some point we have to have a zero. So in words, the most important part is that it has to be continuous. If a function is continuous, and we have some point on the function that equals a negative, and another point on the function, so we'll call it b, that equals a positive, then we have to have a point in between that equals 0. And the reason this happens, if I give myself a little bit more room here, if I look at a picture of a graph, and I have some f of a, so we'll say here's a, here's b. F of a is a negative number. That means f of a is somewhere down here. And remember, f of a is just our way of saying our y value at a. So that means my point at a is in the negatives. My point at b is in the positives. In order for me to get from point A to point B, in order for me to connect those with a continuous function, there is no way for me to connect these without crossing 0. So I have to at some point cross the x-axis as long as the function is continuous, because I can go in a straight line. Even if I travel along, I'm going to cross over the x-axis. So this theorem just says that if I have a negative number and I have a positive number, at some point in between there, my continuous function has to cross 0. So it's just a way for us to check if there are possible zeros in a polynomial without having an equation or without having the graph in front of us. It's just another way for us to check to see what we could possibly be working with. Maybe we do have a 0, maybe we don't have enough information to tell. We might even have more than one, because if you see, I don't know, my graph could cross over, I could bounce back, cross over again, and I can get to B. So I could have more than one 0, but the intermediate value theorem tells us that we have to have at least one 0 in between those 2 points. So what this looks like is I could ask you to use the table to determine where the zeros are in this continuous function. So basically, I want to look to see where my y values are switching from positive to negative. So when I look at this table, My x values don't matter because that's just my location on the graph. It's my y values that I care about. My y values are telling me if I'm switching over from above the x-axis to below it or vice versa. So I'm just going to look and say, okay, from -6 to -2, I'm still in the negatives, not enough information to tell. But from -2 to 3, I'm going from below the x-axis to above the x-axis. So I have to have a 0 there. From 5 to 1, I have to have a 0. And then from -2 to 2, I have to have a 0. If you don't believe me, we can plot these. Let's get ourselves a graph. Just to double check to make sure we know what we're talking about. So if I'm going to graph these, let's see. Draw my x-axis. Draw my y-axis. Then I'm going to plot the points. I've got -2, -6. Then I've got -1, -2, 0, 3, 1, 5, 2, -1, 3, -4, 4, -2, and 5, 2. So if I go in and connect these dots that I just plotted, I can see a picture of my graph, and I can confirm that I have a 0 in between -1 and 0, just like I said here. I have a 0 in between 2 and 1, which is what I saw here, and I have a 0 in between 4 and 5, which is what I saw here. So in order to answer this question, I would say I have zeros between -1 and 0, 1 and 2, 4 and 5. Because remember, when we answer our questions, we use our x values, but I used my y values. I looked to see where my y values were changing from negative to positive or positive to negative in order to decide, but then I used my x values to tell which interval that was happening on. I could also write these as -1 to 0 if I wanted to be more mathematically correct. I could write them as intervals instead of using the word and. So if I give you a table, you're just looking to see where the y values are changing signs, and that's where you're going to have at least 1 0. Could have more, but you have to have at least 1. So super important that the graph is continuous and that they tell you either the graph is continuous or that they give you an equation that you can check to see if it's continuous. And continuous just means the whole thing is connected. Because if I ask you, does the graph of f of x equal -x have any real zeros? If I graph that graph, that's everybody's favorite. It's the one that has the two pieces and you panic a little bit when you see it. 1 over x, our reciprocal function, is a graph that looks like this. And this graph is not continuous because it's two pieces. It's not connected. I can't draw the whole thing without lifting my pencil up. And I see that it never crosses the x-axis. So because this is not continuous, I'm able to be over here in the third quadrant, and then I jump and continue on in the first quadrant. And I skip crossing the x-axis. I never actually cross it because the graph is not continuous. So since f of x is not continuous, the intermediate value theorem, which you can abbreviate IVT, intermediate value theorem, does not guarantee any real zeros. It has to be continuous, because we can see I have negative values over here, right? And I have positive values over here. But even though I have negatives and positives, the graph isn't continuous and it skips right over 0. So it has to be continuous. So then I could tell you even less information than a table or an equation, and I could say, given a continuous function f of x, and knowing f of -1 is 4 and f of -2 is 3, does the IVT guarantee a real zero? So to kind of get a better idea, let's draw ourselves a picture and say, okay, f of -1 equals 4. It tells me I have the coordinate -1, 4. So I'm going back 1, up 4. I have this point. -2, 3, back 2, up 3. So now it's a continuous function. I could potentially have a graph that goes like this, but I could also have a graph that just connects these two. So there is not enough information here for me to decide if there's a real zero. I could have also just looked and said, okay, positive y value, I need a positive and a negative in order to guarantee a zero. So since f of -1 is positive and f of -2 is positive, the intermediate value theorem does not guarantee a real zero. One has to be positive, one has to be negative in order for it to guarantee a real zero. The last kind of question I could ask you is to prove it or show mathematically and explain why the function f of x equals x cubed plus x plus 1 has a zero on the interval 0 to 1. So the first thing I want to find if I'm solving this problem, I want to find f of 0. So plug in 0, I get 0 cubed plus 0 plus 1, which just gives me 1. And then I want to find f of 1, because I want to know what my y values are at those 2 points. Because these are my x values that they gave me. I need to know if my y values are positive and negative. So then I plug in 1, and I get 1 cubed plus 1, which gives me 3. And when I look at this, 0, f of 0 gives me 1, f of 1 gives me 3. Both of those are positive, so I do not have the ability to guarantee a 0 on this interval. So since both f of 0 and f of 1 are positive, the intermediate value theorem cannot guarantee a real zero. If I solved this problem and one of them came out to be negative, then I could say that it would guarantee, because I have to have a positive and a negative. So let's try this one. Does the IVT guarantee a real zero for the interval -2 to 1? So I'm going to plug in -2, and I get negative. Protection is important, remember, so make sure you use it. -2 squared minus 1. When I go to simplify this, actually I'm going to go down instead. I get -2 squared I have to do first. I have to square it first and just kind of bring the outside negative along. -2 squared is just 4 minus 1, but this is really -4 minus 1, so it's really -5. Then I want to find f of 1, so I get negative, parentheses, 1 squared minus 1, which gives me negative 1 minus 1 gives me negative 2. So now I look at my y values and say, okay, I've got negative 5 and I've got negative 2. They're both negative, so that does not guarantee a 0. So since f of negative 2 and f of 1 are negative, the IVT does not guarantee a real 0. So basically, if they give you a table, you're checking the y values to see where they're switching from negative to positive. If they ask you to decide if it's going to guarantee a 0, you're plugging in the endpoints, checking the y values of the endpoints to see if you have a negative and a positive. If you have a negative and a positive, then it guarantees it. If they have the same signs, so if they're both positive or they're both negative, it does not guarantee it.